time to get started. Come find a seat. It's my great pleasure today to introduce the rollerblading state champion for tricks in Michigan, Daniel Erman. Daniel pursued this unusual path to mathematics a bit further. He was an undergraduate at Brown, then worked at the Education Development Corporation in Boston, and finally decided that after all, research mathematics was a good thing, and came and did a PhD in Berkeley with me. Got his degree in 2009, did postdocs in Stanford and Michigan, climbed the ranks in University of Wisconsin, won research and teaching prizes there. I think it must be something that rubbed off from that early education work. I looked up rate my professor, and the very first comment was, Erman is seriously the best professor I've had at this school. Well, okay, this school. He cares about his students and communicates the subject, and his passion rubs off on you. He made an important discovery in the pandemic, namely that life is pretty good in Hawaii, and he moved now to the University of Hawaii. He has a big range of interests, which this all suggests. His most cited paper is about Hilbert schemes of 8 points, very concrete matters. He did lots of work on syzygies, now most recently toric varieties and virtual things. And true to form, being broad and interested in many things, he's going to talk today about Hilbert and mirror symmetry. Daniel.
All right. Thank you all for coming, and thank you, David, for that lovely introduction. I'm going to talk today about an area that's been developing over the last decade, and really in force over the last several years, and it has to do with multigraded syzygies. And I'll start with some of the history of syzygies, dating back to Hilbert, and then I'll move into what the multigradings, the challenges that are posed by multigradings, and some of the observations we've had that have helped us overcome those. So starting with Hilbert, Hilbert's use of syzygies came from invariant theory, which was a classical algebraic question. You have a group acting on a ring, say on a polynomial ring. So I'll start with just a simple example. Let's take a cyclic group of order 3, and let's act on a polynomial ring. Or what I'll do is I'll use the generator of the cyclic group. We'll rescale the variables by a third root of unity. And if you take this action, you can start finding some invariants. U cubed will be invariant, because if you cube that coefficient, it'll cancel out. And V cubed will be invariant, and so on. You can quickly find 4 basic invariants, and there they are. And with a little more work, you can maybe convince yourself that every invariant is going to be a polynomial combination of these guys. So, u to the 6th, u to the 9th, so on, various combinations. And the idea for how to study them is to start comparing it with a polynomial ring. So I've got 4 basic invariants, and so I'll introduce a polynomial ring with 4 variables. And I'll do a surjection. I'll take the first variable x, will map to u cubed, and so on. And now, the generators here are not independent. If you look, say, at the product of the 2 red invariants, u cubed and uv squared, that's the same as what you get if you take the blue invariant and you square it. Right? And so that translates to a polynomial relation. So xz is the same as y squared. And there are several such relations. If you substitute the invariants, it's not hard to check that each of those is a valid relation on the invariants, the way we've set it up. And so we've got our generators, we've got our relations, but unlike, say, with abelian groups, this isn't the end of the story. There are higher relations. So the relations themselves satisfy a relation. It's a little harder to say this, but I tried to indicate in color. So if you take that blue column vector and you multiply, you take the dot product with the relations, you'll get 0. And I don't know, it takes a minute, but if you look it out, you look the first expansion, you have an xwz, and there should be a negative xwz later on, and there is, and they kind of cancel term by term. So you can find these higher relations, and I've listed 2 of them. And at this point, for this example, this is the end of the story. Those higher relations are independent of one another, and what I have here is a free resolution. The word syzygy is a word that's meant to capture this generalized relations. So in more complicated examples, you could have relations on relations on relations, or so on, and so we use the word syzygy as a catch-all for that term. So the relations are the first syzygies, and then so on. The idea behind this method is you want to take an object which could be very complicated. I mean, this was a baby example. My invariant ring wasn't very complicated. But if you have a complicated group acting on a polynomial ring and lots of variables, you can get a complicated invariant ring. And we want to understand the structure of something complicated like that. And this process of syzygies converts the study of this complicated thing to a finite collection of matrices of polynomials. So it's a little bit like reducing it to linear algebra, but with polynomials, but that's, that has some complexity in its own. There's one other observation I'll make before we leave this, which is for a number of the things that they cared about in invariant theory. So some of the questions would be very concrete. How many invariant polynomials of degree 27 are there? What's the dimension of that vector space? What about dimension? What if you look at degree 30 polynomials? How many are there? For those sorts of questions, often it turns out you don't need to even know the polynomials that appeared in the matrices. All you need to know is the size of the matrices and their degrees. And so this schematic here, where we've kind of illustrated the size of the matrices and the degrees, that's often enough information to learn interesting things about your ring. And this is kind of the method of syzygies, is studying something complicated by this discrete data, the number of relations and higher relations and the degrees. Now, a little more formally, what I'm talking about is called a free resolution. So a free resolution is a complex of free modules where the kernel of each is the image of the next. The kernel of each map is the image of the next. And the method of computing syzygies amounts to finding a free resolution. And a priori, this process of computing higher and higher syzygies, I mean, it might not terminate. Maybe it's not obvious whether it would terminate or not, but this was Hilbert's insight, was that if you're working with the polynomial ring, if you're comparing to a polynomial ring in n variables, then this process will always terminate. And it'll terminate in at most n steps, where n here is the number of variables. And so what the syzygy theorem is doing, it's giving a universal bound on the length of these free resolutions, and it's a universal algebraic bound. It's based entirely on the number of variables. And this allows one to again, take your complicated thing and reduce it to a finite number of matrices. So this is what Hilbert did, and in conjunction with the basis theorem, it's the foundation of a lot of finiteness results in algebra. And he used a kind of collection of ideas like this to answer a number of problems in invariant theory. And then what happened post-Hilbert was syzygies grew. It became a tool for studying polynomials. And so what we see throughout the 20th century is anywhere where polynomials are popping up, or some of the places where polynomials are arising, syzygies are having an impact. So I'll talk about algebraic geometry in a moment. That's a particularly important set of applications. But syzygies have had real impact on an array of different fields. I mean, in computational algebra, through work of Bayer, Mumford, and Stillman, syzygies are used to understand the complexity of the basic algorithms, the complexity of Grosvenor basis algorithms. Syzygies have been used in combinatorics, work of Richard Stanley on the upper bound conjecture. And I mean, the list goes on. Polynomials appear everywhere in mathematics, and syzygies give a tool for studying them. It's not surprising that you'd see lots of applications. Now, the connections with these topics are not all equal, and I want to focus on the particular connection with algebraic geometry. So here, there's a foundational dictionary between commutative algebra and algebraic geometry. It's the type of thing you'd see in a graduate algebraic geometry course. And the polynomial ring relates to the basic projective variety, a projective space. I guess while I'm here, I should make a note. I'm going to work over the complex numbers everywhere, but one of the nice things about syzygies is that they have a kind of linear algebra feel to them. They amount to studies of matrices, and so they actually work very well with other fields. So for more arithmetically inclined audience members, just about everything I say today works in arbitrary characteristic and really over arbitrary fields. There are a few exceptions, but for the most part, that's true. All right. So in this dictionary, I've got my complex projective planes, say, which is equivalence classes of vectors, x0, x1, and 2, and it's equivalence class under scaling. And this is lining up with the polynomial ring in 3 variables, but to get well-defined polynomial equations on the projective space, you've got to work with homogeneous polynomials, like the one at the bottom. It's a polynomial of degree 3, because such polynomials will either vanish on every point in an orbit or none of them, right? And so if you're working with homogeneous polynomials, that's how you're going to define subvarieties of projective space and so on. I should mention here one other little quirk, which is you can't take, of course, to get the projective space as a quotient in this way, you've got to remove the origin. We don't allow the all zeros vector. That has a degenerate orbit, and so you want to get rid of it. All right. So that's the basic algebra geometry dictionary, and what happened throughout the 20th century and really towards the back is the interaction of syzygies and algebraic geometry became especially robust. So it really became a two-way street. I mean, syzygies were used to prove powerful results in algebraic geometry, and the opposite happened as well. Algebraic geometry was seen to shape what can happen for syzygies. So the algebraic structure of these matrices of polynomials is shaped in a profound way by geometric data. And this became a really positive feedback loop. As we got a deeper understanding of syzygies, it became a more powerful tool, and it kind of reinforced the applications to the array of other topics. So this connection with geometry has been really fundamental to the growth of syzygies. So there's a whole field on the connection between geometry and syzygies. It's the topic of a book by David Eisenbud called The Geometry of Syzygies. And I won't be able to do justice to the whole field, but I have a kind of jumbo slide that's meant to give some indication of what's happening here, right? So I don't know. The way to think of it, on the left, there are an array of classical algebraic geometry topics, positivity and minimal degree varieties, things like this. And there's just this history of theorems that takes geometric data and sees how it can shape what happens or doesn't happen in the study of syzygies. And I want to emphasize a few things about this picture. I mean, one is there's this result of Mark Green. Let's see, can I get it's not working great. The one in bold at the top from 1984. So there's a theorem of Mark Green that I want to talk about for a moment. What he did in his work was he studied curves embedded in projective space. And what he showed was that if they had high degree, if they'd been embedded by a very positive, very ample line bundle, that had an effect on the syzygies of the defining ideal. And the effect is not an obvious one. The effect was that geometric positivity translates to the syzygies being purely linear. You see in those syzygy matrices I talked about, they would consist entirely of linear forms. I want to emphasize this example for a moment. I want to stick with the example for a moment because I think it captures something. I mean, the syzygies are a priori a very algebraic topic. They're matrices of polynomials. And it shouldn't be at all clear that something like geometric positivity is lining up with something like linear syzygies. And it's not the kind of theorem that once you see it, it's easy to prove. It remains a theorem that's difficult to prove. It's a theorem that shows, I guess, how geometry shapes syzygies in a subtle and powerful way. And that was kind of what I mean here when I talk about how geometry shapes syzygies. These are new correspondences in the age-old dictionary between algebra and geometry. And they're ones which were kind of discovered. I mean, many of them were discovered starting with Mark Green's work and the work that followed in the 80s and beyond. So we were still learning subtle new things about interactions between algebra and geometry. And there's one other thing I want to indicate before I leave this slide, which is that a number of the results are recent. I mean, you can see, I think the most recent is 2019. And this remains a very active area of research. There's a community of people who are continuing to take geometric data and try to see its effect on syzygies. Maybe the most profound theorem in here is Claire Voisin's work on Green's conjecture, which was about special line bundles of curves being witnessed by their canonical syzygies. All right, let me move on to the multigraded case. So let's return to this example I had from earlier. So I've still got my cyclic group of order 3, but I've tweaked the action, and I marked in red how I changed the action. So now I'm going to scale by the reciprocal of that third root of unity instead of the original one. And if you do this, the invariants are different. I mean, you still have u cubed as an invariant, and you still have v cubed as an invariant. But you get a new invariant, u times v, because the coefficients cancel. And so in this case, there are 3 basic invariants, and there's one basic relation, and it's x times z is y cubed. And note that it's not a homogeneous equation, or at least it's not homogeneous in the traditional sense. It's homogeneous in kind of a non-standard sense with the degrees as I've indicated. But actually you can do better. It admits a finer, a more detailed homogeneity property. If you grade x with the vector 3, 0, and y with 1, 1, and z with 0, 3, then the equation actually has a z2 degree of 3, 3. It has a multi-degree of 3, 3. And this is richer data. This is more information about the homogeneity properties of that equation. And anyways, this is what I'll mean by multigraded polynomials. They're polynomials that have homogeneity properties instead of with respect to a z grading with something like a z2 or a z3 grading. They pop up naturally in examples like invariant theory. Most importantly, they pop up in the study of toric varieties. So this was work of David Cox. What he did in the 90s was he showed that this classical dictionary between the standard graded polynomial ring and the projective space, he showed that it generalizes in tremendous generality, where if you take essentially any ZR grading on a polynomial ring, you can attach a geometric object to it, and it's something called a toric variety. And toric varieties can be built as quotients of group orbits, just like projective space, but the definition's a little unruly, so let me instead just do an example. So if I take a polynomial ring with 2 sets of variables, like I have over here, and I give the x's a 1, 0 grading, and the y's a 0, 1 grading, then the corresponding geometric object is a product of P1s. So it's a product of projective spaces. And toric varieties include all products of projective spaces and many other examples like this. Now under this grading, if you have a product of P1s, then it's these Z2 graded polynomials, these bi-graded polynomials, which are going to be used to cut out subvarieties. So on the bottom, I've got a polynomial, let's see, it's degree 2 in the x's and 3 in the y's. So it's bi-graded of degree 2, 3, and that's how you get your subvariety. I'll note here, there's one wrinkle that's a little more complicated than in projective space, which is if you think of a point in P1 crest P1 is a 4-tuple of coordinates, x0, x1, and so on. You've got to avoid allowing either both of the x's to vanish, because if that happens, you wouldn't get a good point in the first factor. And you need to also avoid having both of the y's vanish. If either of those happens, you're in trouble, and that's the irrelevant locus. You'll have a bad choice. All right. So polynomials show up throughout a bunch of areas of mathematics, and multigraded polynomials are polynomials with some extra symmetry. It's maybe not shocking that multigraded polynomials will show up in a huge array of examples. We saw one in invariant theory. I mentioned algebraic geometry, but I mean, the list goes on. If you blow up the projective plane, you get a bigrading. I've seen examples in applied algebra, in the modeling of robotic arms, or in multi-view cameras. Multi-graded polynomials naturally appear. There are examples from combinatorics, like the equations of Hilbert varieties. I mean, it's not hard to find an array of examples where multigraded polynomials appear, and that leads to what I think of as a big goal, or this is something that I got interested in, which is, can we build a theory of multigraded syzygies that will have the sort of impact on multigraded polynomials as they arise in all of these fields? Can we, I want here, I mean, let me be careful about what I want here. I don't just want to take the algebraic theory of syzygies and staple multigradings onto it. I want a theory that genuinely offers meaningful impact to all of these topics where multigraded polynomials are showing up, and in a way that's deeper than what you'd get from the original theory, right? And as part of that, I would want it to have an especially robust interaction with algebraic geometry. I'd want to be able to see geometric information in such a theory. Let me say it another way. There was this jumbo slide of geometry of syzygies I had up earlier, where classical geometry was impacting syzygies. And what we got interested in was, can you develop a geometry of multigraded syzygies? If you have this multigraded case and these toric varieties, can you find similar theorems where geometric data is giving us subtle and powerful theorems about multigraded polynomials? And so this is the project that I've been working on with a number of collaborators, Christine Burkish and Greg Smith, and then Michael Brown as well. And so when I talk about my kind of own work in this, it'll all be collaborative with subsets of these individuals. As we sunk our teeth into the project, we came across something that at least at first was a bit of a mystery. So I want to, this is where this is really the heart of the matter. So let me take a minute here. So a multigrading has more structure than a regular grading, right? A Z2 grading is more data than just a Z grading. And so on the surface, we want theorems in the multigraded case that are going to be better than the theorems in the standard graded case. That's natural to expect when there's more structure. But what we observed was that just kind of wasn't the case. The theorems that were out there were the opposite. They were either just the same as the standard graded theorems, or in many cases, they were weaker. And this was something of a mystery to us, or maybe a challenge. We said, how can we build a theory that really capitalizes on that multigraded structure? Said another way, it's this extra data of a multigrading was there, and what we needed to figure out was how to leverage it, how to get stronger theorems in this situation. And in the rest of my talk, I'll try to outline the ways in which we did that, the ways in which we used constructions to get at exactly that question. All right. So the first principle we realized along the way was that we needed to rethink some of the algebraic definitions. So here, let me give a metaphor. I mean, so what happens when you pass from the standard graded case to the multigraded case, what you find is that certain definitions separate into different branches. And I mean, I think this is actually something that's familiar in a lot of areas of math. Here's the example that I decided to focus on, think about prime factorization of the integers, right? You take an integer, it has a unique factorization into primes. Now, if you pass from the integers to a more complicated ring, there are really two notions of factorization that you can think about. You could talk about factorization of elements or factorization of ideals. And those theories pull you in different directions. And so if you're looking to generalize something like the fundamental theorem of arithmetic, you've got to ask yourself, well, which way do I want to generalize it? Which of those branches is the one I'm focused on? And this was happening in the theory of syzygies. There were ideas like basic definitions of the theory, like the definition of a linear syzygy, which played a key role in Mark Green's work. And if you examine that notion in a multigraded case, there are several distinct possibilities about where you could go. And so this created some opportunity. You know, there's genuinely new things to explore, but it also created something of a challenge. I'll note here, I have McLagan and Smith here. I first saw this idea in their paper in 2009, where they analyzed exactly this situation for an invariant known as Castelnuovo-Mumford regularity. So with Burkish and Smith, we looked at the notion of a free resolution. And we realized that there was a very closely related notion which seemed to behave a little differently in the multigraded case. And it's something we called a virtual resolution. And what it is it's still a free complex, but you weaken the exactness hypothesis just a little. So you allow a limited amount of homology into your complex, homology that's supported on that irrelevant locus we saw earlier. At a kind of high level, you can think of it as it's like a multigraded analog of a free resolution. It's geometrically exact. If you want to get a little more precise, what it is, it's a free complex where when you restrict it to the toric variety, it becomes a resolution of sheaves. It's a line bundle resolution. So it's closely related to a free resolution, but not quite the same. But what we discovered was for projective space, the theory of virtual resolutions and free resolutions is almost identical. There's no meaningful, really, distinction between the two there. But when you pass to other toric varieties and multigradings, the theories really separate. And this presented an opportunity. And it's one that we realized could open the door to some stronger theorems. And so what we conjectured was that, here I have it, I'll parse it in a sec, but it's something like a strengthening of Hilbert's theorem. So let me take a moment and parse this. So the setup is, I've got my multigraded polynomial ring, and it corresponds to a toric variety. And then I'm going to try to do Hilbert's syzygy theorem. I'm going to look at a finitely generated module and ask about a uniform bound for the length of a resolution. But there's a tweak. I'm going to do a virtual resolution instead of a free resolution. And what our conjecture was that if you exchange that hypothesis, free resolution for virtual resolution, you can improve your conclusion. You can get a bound, the dimension of x, which is geometric in nature, as opposed to Hilbert's bound, which was algebraic. And let me try to illustrate a little how it compares. So if I take just a projective space, like a 10-dimensional projective space, the difference in the bounds is very small, and in some sense it's even smaller than it looks, which is the 11 is kind of fake. There's some other tricks you can do to say for interesting examples, geometric examples, you'll never even hit 11. So in projective space, we're saying very little. But as you add complexity to the toric variety, the virtual bound and the Hilbert bound start to separate. And so at the far end, you can see a product of 10 P1s. Hilbert's bound would be 20, that free resolutions have length at most 20. And we said you can do much, much better. If you work with this multigraded analog, you can find virtual resolutions of length at most 10. And for the sorts of applications that one wants, shorter resolutions are better. They allow for a simpler analysis and simpler formulas. But maybe more to the point, this is the first glimmer of how to get around that mystery I mentioned. I mean, it's we wanted to find stronger theorems in a multigraded case, things which really leverage that extra structure. And our conjecture was that this was one such example, right? This strengthening of Hilbert's syzygy theorem is only possible in a multigraded scenario. So we conjectured this partly based on a huge array of examples we computed and partly based on the fact that we found a proof of it for products of projective spaces. But we conjectured it for arbitrary smooth toric varieties. And actually, I should say, there was something in the air around this time. I mean, there were kind of other results that were looking at novel analogs in the multigraded case and starting to find slightly stronger results. So I think on my last slide, I had a couple mentioned. But this is kind of one example of that happening. And years later, we found that it was related to a difficult conjecture of Orlov. So Orlov had a conjecture about generating the derived category of a smooth variety, and at most dim x steps, the at most dim x is notable. And in the toric case, that conjecture is very closely related to ours. I mean, neither implies the other, but they're both very close in spirit. And there were groups of people working on both conjectures. So as of January, let me get the year right, January 2023, there were groups working on our conjecture and on Orlov's conjecture. And so the special cases of our conjecture that were known, there were several of them listed below. Maybe I'll highlight a couple. Jay Yang proved our conjecture for arbitrary monomial ideals, for monomial ideals on an arbitrary toric variety. So he proved it for a kind of special class of algebraic objects, but any toric variety. Brown-Sairafi proved it for any module, but on special toric varieties whose Picard rank was 2. And so we were getting some special cases coming in. There were also a number of special cases of Orlov's conjecture. Maybe the most notable one is the Ballard-Favero-Katsarkov one, which proved Orlov's conjecture also for toric varieties whose Picard rank is 2. So those are projective bundles over projective spaces. But as far as this conjecture, this is where things stood. We'd introduced a new algebraic notion that was only really useful in the multigraded case, and we were conjecturing that this new multigraded construction would open the door to stronger multigraded theorems. But by and large, it remained open. And maybe I'll comment for a moment on why it was difficult. So I think there's a couple reasons why it was difficult. One was the obvious reason, which is, I mean, there was a whole literature on free resolutions that you could capitalize on if you were solving free resolutions. They'd been studied for over 100 years, and we introduced a twist on that, these virtual resolutions, and it was something new. We just didn't have the kind of foundational literature. So there were a lot of tools and ideas that were just remained unexplored. So some was just the novelty. But the other challenge was, it's not totally clear in our conjecture how to make use of the geometry. I mean, the bound is a geometric bound, so the geometry is expressing itself, but it's not totally clear how to do that. And that's a problem that was unlocked by work of some other individuals. So the story deepens a little. So what happens, the second principle that we found for unlocking the multigraded structure was to incorporate a connection with symplectic geometry. So let me give an overview here. So the idea is this, that in physics, mirror symmetry was a theory that observed a surprising duality between certain physical theories. You'd have, one physical theory and another, and they'd make the same predictions, and they were dual in a certain way. And there was an effort by mathematicians to try to understand this and give it a rigorous foundation. And one of the famous attempts was Koncevich's homological mirror symmetry, which was a series of conjectures he had that linked algebraic geometry and symplectic geometry. So more precisely, the conjectures linked a derived category of sheaves in the algebraic geometry world with a Fukaya category in the symplectic geometry world. And homological mirror symmetry is a robust area of research still. There's tons of open questions in it. There's a lot that remains unknown. But one really important case that's known is the case of toric varieties. That was proven by Mohammed Abu Zaid. And so what we have is we have homological mirror symmetry for exactly the geometric setting that's feeding into the multigraded algebra. And so there's more geometry in our picture, and incorporating this was the key in the proof of our conjecture. So this slide, the thing at the top is just the old conjecture, but I changed the word conjecture to theorem. That's why it's in red, and I changed the names from me to the people who proved it, right? So it's Hanlon, Hicks, and Lazarev, three researchers who are working primarily in symplectic geometry. And they actually, before I get to their method, let me say what else they proved. They proved a lot. They also proved that toric conjecture of Orlov I mentioned. They proved a related conjecture of Bondel about generating the derived category of a toric variety with a certain canonical set of line bundles. They took Bailenson famous work about resolutions of the diagonal, and they showed that generalized to all toric varieties, and in a way that also massively generalized work of Bayer, Popescu, and Sturmfels on resolutions of the diagonal for toric varieties. And they even proved a structure theorem for what happens if you embed one toric variety into another, and it was a strong structure theorem that I think no one had expected, right? They proved, it's really a tour de force of a paper. And the fundamental idea was to take constructions from symplectic geometry, and they were constructions based on Morse theory, and bring those into the algebraic world. So they're bringing new geometric insights and tools to bear on the algebraic world. And this connection, this direct connection between symplectic geometry and commutative algebra was what they needed to crack a lot of these conjectures. Let me say, again, it's like there was something in the air. So around this same time, there were a number of other authors doing kind of similar things. So I'll highlight the work of Favero and Huang, which also came out in early 2023, and they similarly took ideas from symplectic geometry and brought them to the algebraic world and proved a number of the conjectures I just mentioned too. So they proved, they proved the Orlov and the Bondel one, for instance, from their work. Reggie Anderson was doing work inspired by homological mirror symmetry and looking at generalizations of the resolutions of the diagonal, and his work borrows ideas from homological mirror symmetry to generalize that work of Bayer, Popescu, and Sturmfels. So similar ideas were happening. Michael Brown and I have a paper where we proved some of the results via other methods in this way. But the legacy of this collection of results is it's like this third leg of the triangle. What happened is we started to see not only how to put symplectic geometry into conversation with commutative algebra, but we thought there's real power in doing that. Incorporating kind of a novel geometric perspective really offered powerful new tools and new perspectives. All right, so the last of the principles I want to talk about is making use of all of the geometry. And for this, I've got to correct the record slightly. So I've been talking so far about how a toric variety corresponds to a multigraded polynomial ring, but that's a little bit of a lie. I've oversimplified it. So what actually happens is it's a several to one correspondence. There are several distinct toric varieties which all correspond to the same multigraded ring. And note, this is different than the projective space case. So I see this as an opportunity and a challenge, right? I mean, the opportunity is, in some sense, we can see more geometry. There are multiple geometric objects which are feeding into our algebraic picture. But there's a challenge, which is how do we synthesize that, right? I mean, in the classical picture, you have a graded ideal, and it corresponds to a projective variety, and you look at that variety, and its properties are supposed to line up with the algebraic properties. And here what we have is a situation where a multigraded ideal will correspond to a finite collection of subvarieties of a finite collection of toric varieties. And so there's a challenge. How do we synthesize and make use of all of that data to learn new things about syzygies? It's actually even richer, right? If you incorporate the mirror symmetry, you get every one of those toric varieties has its own mirror, and you want to incorporate all of that geometric data too. And so what we're seeing is a setup where we've got this array of geometric objects which are all influencing the multigraded algebra, and we want to figure out how to capitalize on that. Let me say, the principle, I think it's appeared in different places. As far as applications to syzygies, I think the first place where the idea was used to get new insights about the structure of syzygies was a paper that Michael Brown and I wrote about the BGG correspondence, where we kind of used the finite list of toric varieties to get some properties. But it's one of these principles, once you see it, you can't unsee it. I mean, of course we need to make use of all of the geometric information. And so what's emerging now is an answer to this earlier mystery. So the earlier mystery was, how do we make use of the extra structure? How do we make use of the multigraded structure? We should expect stronger interactions with geometry because there's more data here. And here's the kind of roadmap that's emerging. And I've listed, this involves papers and work in progress of a bunch of people. But the roadmap that we've come up with it's this triangle of fields. And so let's take a minute and talk about it. In the commutative algebra part, remember that the commutative algebra has changed. We've been introducing new notions that are kind of unique in the multigraded setting. And so that was one change we had to get to this roadmap. The second is we've added symplectic geometry to the picture, and we want to incorporate all the data of those Fukaya categories into one. And in some sense, it's like we want to glue or combine the various categories, the various symplectic categories into one thing which will synthesize all of the data. And here I want to highlight that the idea of how to do that is work in progress of Favero and a postdoc, Jesse Huang. They've been kind of leading the charge in how to get a total object from that finite set of symplectic data. In the toric case, we want to do the same thing. We want to find a way to synthesize the geometric contributions of our finite list of toric varieties and kind of glue them together into some sort of package. And this is work in progress of myself and Michael Brown and another postdoc, Lauren Cranton-Heller. We've been working on kind of how do you combine derived categories of birational varieties in a way that keeps their essential features. And then these arrows, how these pictures all interact, are work of all of the other individuals I've listed here. I've been exploring kind of how to deepen those interactions. I do want to highlight one more name, which is Andrew Hanlon, who's also a postdoc. He came from symplectic geometry, and he's really been fundamental in helping the group of researchers listed here kind of understand how to communicate with one another. He's really done some spectacular work. All right. So our goal was to develop this geometry of multigraded syzygies, this sort of picture that would parallel the classical story. I wanted to have a theory where classical algebraic geometry topics are giving us insights into the properties of free resolutions and the properties of multigraded free resolutions. And as we've built up the foundations and kind of understood how to put these topics in conversation with one another, that's actually been starting to happen. And so over the past several years, more and more, especially over the past several years, more and more results in this vein have been coming online. And we've been seeing more and more connections between classical topics in algebraic geometry, and specifically subvarieties of toric varieties, and the effect that those have on the multigraded picture. I don't want to give a false impression here. I mean, there's nothing at the depth of Voisin's work on Green's conjecture, right? But there genuinely are novel multigraded analogs of a lot of the theorems that the geometry of syzygies was built upon. So let me end by just highlighting a few of these contributions. So the sheaf cohomology arrow, the very top arrow, in the classical story, there's a connection between vanishing of sheaf cohomology and the degrees that appear in your syzygy matrices. This is known as the theory of Castelnuovo-Mumford regularity. And it was that algebra geometry duality was laid out in the famous theorem of Eisenbud and Goto. But it doesn't work in the multigraded case. There's a genuine difference between the geometric and the algebra sides. And at first, it seemed to be they seem to be fundamentally separate. But what we've seen in the last, I guess it's 15 years since McLagan-Smith's work, is as we better understand the algebra side and we work with kind of novel definitions and we better understand the interaction with geometry, we're starting to find ways to reconcile that algebra geometry picture in the context of say, sheaf cohomology. And so there's an array of ever stronger theorems here that link those two sides. If you look at the very bottom arrow, it's about geometric positivity. There are a couple papers I'll maybe mention. One is the paper of Michael Brown and myself, where what we showed was we asked whether Mark Green's principle, can geometric positivity inducing linear syzygies, is that a thing that makes sense in the multigraded setting? And what we did is we proved that the answer is yes, at least for curves in weighted projective spaces. So it's kind of a first step towards trying to move Green's theory into the toric world. Minimal degree varieties are another classical topic, which date back to Del Pezzo, and have been understood in terms of work of Eisenbud and Harris from the 80s, and, Eisenbud and Harris's work recast the classification theorem in terms of syzygies, and so we wondered, can one start to classify minimal degree varieties in these new settings? And there's new work of Banks and Ramkumar, a graduate student and a postdoc, which are doing this for varieties of weighted projective spaces. And so what's happening, we're getting more and more of these connections between the geometry and the syzygies. And they're exactly of the sort we'd hoped for. They're sorts where subtle geometric properties are shaping the multigraded free resolutions in powerful ways. And it's an evolving field. Slide is meant to illustrate, it draws from researchers from commutative algebra, algebraic geometry, symplectic geometry, and more. But it's one where more and more results are coming online, and it's been a really exciting thing to work in. All right, so I'll stop here. Thank you all for your time.
Thank you for that very wide survey and interesting talk. There's time for some questions if people would like. There are a couple of microphones. There's one over there, one over there. If you want to be heard asking your question. Otherwise, I think, oh, there's a question, yes.
So you said you want to use all of the geometry, and this, I guess this is kind of what you mean, but do you have any other ideas for what that could mean?
Yeah, I mean, so it's a little tricky, and if I'm being perfectly honest, some of the successes we've had are in situations where there is still a one-to-one correspondence between the toric variety and the ring. It's certainly easier. So weighted projective varieties appear in some of these results for that reason. But that said, there are glimmers of results that make use of all of it. So there's work I mean, some of the work in progress I'm referencing shows that and actually this predates in some ways, but shows that if you want to understand the derived category, knowing the contributions from that whole finite list makes it simpler. And so for the structure of things like the derived category, combining the contributions from the various varieties is essential. Another thing that you can see is let me think of another good example. I mean, if you're trying to understand how say, the geometry affects I'm struggling to think of a good example, but that's the overarching thing. There are some glimmers where the multiple geometry contributes, but for something like a Green's conjecture or a Green's theorem, how that works when there are multiple toric varieties remains a complicated question. Yeah, it's a good question.
We have another question over here.
Yeah. In the early case, you talked about Morse theory from the homological mirror symmetry to the commutative algebra, but there was no more Morse theory at the end. Can you say anything about that?
Yeah, sure. I mean, so partly this is my own taste. I'm a novice at learning symplectic geometry and some of these topics. Let me say, so here's something that happened. So our conjecture about the length of a resolution was at most the dimension of x. And we based that, we had some algebraic heuristics for that, and we based it on a lot of evidence. So what these folks, Hanlon, Hicks, Lazarev, did was when they brought in Morse, they used Morse functions on the symplectic side and then passed them kind of through the mirror, or looping around to the commutative algebra. What our bound amounted to was something like the following, which is a fact, which is that a Morse function that's sufficiently generic will have at most dimension x critical values. And that fact gets translated through the situation into exactly our bound on the length of the resolution. So that's kind of how it was happening there. They were building a dictionary where from a Morse function you could get a free complex. And what we're trying to do now is really understand that, because from the types of Morse functions that they're using tend to create very combinatorial decompositions, and we want to translate that to free resolutions a little bit like, I don't know, how one in Stanley Reasoner theory computes combinatorial data to algebraic data. So I mean, one of the challenges we have is how to do what they did in a more systematic way rather than just for the system of examples they needed it for. But I don't, yeah. So I mean, that's one of the next steps, is can we bring the kind of Morse theory constructions from symplectic geometry to commutative algebra into a more robust theory? But that's next.
Thanks.
Yeah, sorry, that was a long answer.
Another question over here.
So like essentially like you're creating kind of a new tool in mathematics. So like I'd like to ask you, like, would you think that there would be some like usage in like physics, and like what do you think like ultimately it's gonna reveal about like existing like geometric structures that we know? Because like a lot of the work I see is trying to link it together, but like sort of where do you think it's gonna lead to?
Yeah, it's a great question. I mean, multigraded polynomials are showing up in lots of places. And so if you can build a tool that tells you something new about them, it's going to have an impact. And that's really our hope, is that we can do something genuinely new on that boundary. And there are some glimmers of that, but it's we're nowhere near the sort of impact that standard graded syzygies have had. As far as connections with physics, that goes a bit beyond the things I know about. I mean, there's work that has tried to connect notions from syzygies to other notions that arise in string theory. But that's a little outside the things I know, so I can't speak as much to that. What I will say, though, is as far as major applications, I would hope that we could use the shorter resolutions suggest that there's ways to capitalize on the multigraded data. And I would hope that we could use that to improve computational algorithms in the multigraded case in really fundamental ways. And there are even some glimmers using the BGG correspondence that show how to do that in some limited cases. But I would hope that that's the sort of impact we might be able to have, is by demonstrating new structures, we can capitalize on those to speed up some of the computations we care about.
On the other side of the room, Karen.
Yeah, thanks, Dan. It was an interesting talk. I have a much more mundane question. You might have said this and I missed it, but you have your toric variety and you associate a ZR-graded algebra,
Yeah.
but there's finitely many toric varieties that all give you the same one.
Yes.
So what was that process that produced
Sorry,
the algebra?
I maybe was too loose. It's the Cox construction. So what the grading induces an orbit structure, but you have to remove a bad locus to get a projective quotient. And the question is, which bad locus do you remove? So the difference is each toric variety comes with its own irrelevant ideal, and you're varying the irrelevant ideal. So you have your multigraded polynomial ring, and you can remove different loci and get different geometric quotients. But if you want to just, so in some sense, let me say it this way. If you have a toric variety, what that lines up with is a pair, a multigraded ring and an irrelevant ideal.
Right.
But I want to do algebra. I want applications to algebra. So I want ones that are just about the ring. And so how do we remove the reliance on that auxiliary data of an irrelevant ideal? Well, we look at all possible ones simultaneously.
So that set of finitely many toric varieties that all correspond to the same ring, but different
that's right.
ideas. What do they all, what properties do they all share?
Is there
some way to go from one to the other in some natural way?
It's the Mori decomposition of that's exactly what it is. So it's the secondary fan, they call it in toric geometry, but it's the Mori chamber decomposition. And so you want to understand, I mean, so there are tools to patching them together that I originally was going to do that, but I was worried about time. But so there are tools from birational geometry about how to study that collection all at once. And what we're introducing some new tools, and we're borrowing some of the old ones to kind of synthesize the information.
Okay, thanks. Yeah, that answers my question.
All right, I think we can adjourn to room 204. Anyone who wants to go on chatting or just chat loosely with Daniel is welcome to join us there. Thanks again for the talk.
Thank you, David.